We've now written an equation that tells me the thing that I want, the area, in terms of a single variable. Here, my independent variable is x, which was the length of fencing running, say, north to south in this picture. So depending on what x is, I can just calculate what the area of that fencing is going to be. And, oh, this formula, my area function, it's a polynomial. I like those. Polynomials are continuous. Polynomials are differentiable. Polynomials are very nice functions to be working with. So I want to optimize and find the most amount of area I can contain in this situation. So what am I going to do if I want to find the maximum value here? Well, ultimately, I'm going to be checking my derivatives. But I do need to keep in mind that this equation only makes sense for certain values of x. The whole premise of this situation is that I only have 2,400 feet of fencing to work with. And again, it's a little contrived in this example, but when you're using this stuff for practical problems, you need to be aware of your constraints. You need to know what's the absolute boundary of where I'm allowed to look for solutions. It doesn't make sense to pick an x larger than 1,200 in this situation, because if I pick an x too large, then my y will be forced to be negative. And likewise, I can't pick a negative length of fencing here. So I have this boundary to check. The very smallest x I could have is 0. The very largest x I could have is 1,200. Now I can go ahead and do my derivative. Derivative of this function is going to be a prime of x for the derivative of a. And that formula is going to be 2,400 minus 4x. I need to find where that derivative equals 0 in order to test for my critical values, right? This derivative is defined everywhere, so I don't need to worry about whether or not it is undefined anywhere. And what do I get? X has to be 600. So this gives me 3 numbers to check. I will check x equals 0 and see if that is the most amount of area. I will check x equals 1,200 and see if that's the most amount of area. And then I will check x equals 600 and see if that's the most amount of area. All 3 of them are candidates to be the maximizer. So let's go ahead and try running these through the formula. A of 0 is 0. Okay, no, I don't want to fence in 0 amount of area. Next, A of 600 is 720,000. Oh, cool. Okay, that's a pretty big number. And in fact, it's bigger than any of the ones I saw in my diagrams where I was sort of playing around with this problem. Okay, that's good. And then A of 1,200 is, again, 0. We'll forget that one as well. So my only 3 places where the maximum could have been was at x equals 0, x equals 600, and x equals 1,200. If I want the global maximum, right, what is the optimum value here? I'll just take the biggest one of these y coordinates that I saw. And that was at x equals 600. Now this bit here is saying that we could have also used the second derivative test. This function is a parabola. Its leading term, leading. Its leading term is negative here. It's just been shuffled into the back. But since I have a negative sign on that x squared, I know this is a downwards facing parabola. It has a single maximum because I know what parabolas look like. And then those other two values we checked at the endpoints are just where it hits the x-axis. So this tells me what is the largest possible area we could have fenced in this way.